everybody, I wanted to do a quick video summarizing free body diagrams for some things moving in a circle, and a roller coaster is the perfect example to demonstrate that. So here we've got a roller coaster, the cart's going to go up and then down and then around and make it over to the other end. And this will be a smooth surface. We will ignore friction. And we're just going to look at a box that glides along the surface. So it glides along surface. So that's the situation that we are going to consider. And in fact, I've got my little box here. It has a mass M1 and it has a certain normal force to it. And I can't change, as we ride along here, the normal force magnitude, the size of that arrow, the strength of that force will change. I can't change my construction paper normal force, but I do want to emphasize how the direction of that changes as the block glides along. It always points perpendicular to the surface. So let's watch just first what happens to that normal force direction as we ride along. It's going that way. At the top of the hill, it points directly up. As we continue to move downhill, it's at an angle. And then we're here. That normal force points directly up again. Then we get here at this part of the loop-de-loop, and we're going around. When we're at this point, the normal force points directly inward. When we are here, the normal force points downward. And then when we're here, it points to the right. And then we continue on our way. The magnitude of that force changes, but the direction is always going to be perpendicular to that surface at any point. I want to highlight the free body diagrams for a few key snapshots along that ride. First snapshot's going to be at the top of the hill. Second snapshot at the bottom. Third snapshot on the side. Fourth snapshot at the top. So those are the four snapshots I want to consider. Now we saw that the normal force here is in the up direction when we're at the top of the hill. Let's identify the circle of curvature the circle that fits this hill, and then we'll figure out its radius of curvature. There's the circle that fits that hill approximately, and we'll call its radius capital R1. And we'll say the block has a speed v1 here, and then v2 there, v3, v4. But I'm not going to draw that in because I want to draw free body diagrams, and velocity arrows don't belong on free body diagrams. I have my reference frame we're going to use here. We're going to choose a direction that's radial toward the center of the circle as one positive direction, and then tangential as the other positive direction. So here that looks like, let's see, radial is downward. There's the reference frame choice we're making for this scenario. To point toward the center of the circle, we need to point downwards. And we know that when we're moving in a circle, the net force must be in the radial direction, meaning that there's more force in this example down than there is up. So we have a certain gravitational force, which I'll call Fg. And then we have an upward normal force we saw, but that normal force must be less than the gravitational force. The gravitational force must win because the net force needs to point toward the center. I'll call this normal force 1 because we'll have more normal forces as we go. So there we go. The box continues to ride along, and now it's at the bottom of the hill. The normal force still points up, but we need to identify the new circle that fits this point at the curve. That circle is right here, and it may have a different radius than the first one, so we will call it radius 2. And I can see that's going to be in the way, so I'm going to move it to over here. What do the forces look like? We've got that upward normal force. Gravitational force points directly toward the center of the Earth, but now the normal force must be the one that's greater because we need a net force toward the center of the circle. And the gravitational force didn't change. It still is the mass of the block times the Earth's gravitational field strength, little g. And now I'm going to choose, let's see, the radial direction in this example is going to be up. So a different reference frame than before, tangential direction to the right. So there we go. The radial direction points upward in this example. All right. As we move along here, the normal force is going to point to the left in this case. This will be N3, and the gravitational force didn't change. It's pointing directly downwards. And it's moving upwards, but there is no force in that direction because you don't need a force to move. Now, why? Now, how? Here's our block. If it's moving along here, if there were no track, if the upper half of the track vanished, it would continue in a line upwards and then come back down as if it were in free fall. And so this normal force, what it's doing is turning the block so that doesn't happen. The normal force is preventing that upward free fall motion and instead turns the block on its way. Let's talk about situation 4. If we grab our block, at the top, the normal force is pushing down because that's the direction perpendicular to the surface at that point. And so we have two forces in the downward direction, that same Fg and the normal force 4. Both of them point downwards. And let's say this is a circular track of radius. We'll just call this radius r because it fits for both 3 and 4. There's a circular track maybe in this case. All right, so that's what our free body diagrams look like. I'm now going to write the sum of the forces equation in the radial direction for each of these. Starting here, where the radial direction is downward and the tangential direction is to the right. The sum of the forces in the radial direction for scenario 1. What does that look like? Sum of the forces in the radial direction. That's going to be in minus out. Toward the center of the circle was the gravitational force minus normal force 1. And that has to be equal to mass times the acceleration in the radial direction. And we've learned that mass times the acceleration in the radial direction, that is equal to the square of the speed of the object at position 1 divided by the radius of curvature at position 1. So that's what the equation of motion would look like for the object in the radial direction at snapshot 1. This is not something to memorize. This is something that you should be able to figure out from a similar scenario. Number 2. We want to add up the forces in the radial direction. And let's remind ourselves here, radial is toward the center of the circle, which is going to be up for scenario 2. So it's going to be normal force minus gravity. In minus out, always. In minus out. So here, it's normal force 2 minus the gravitational force, which we don't need a subscript on because it hasn't changed at all. And that's going to be equal to m times the radial acceleration. I'm going to call this radial acceleration 2, this one radial acceleration 1. And then we know that the normal force minus the gravitational force then must be equal to mass times speed 2 squared over radius of curvature 2. All right, let's look now at number 3. Number 3, we're going to add up the forces in the radial direction. And let's see, the radial direction toward the center here is left. So I'm going to choose this reference frame where the in direction is to the left. So in minus out is going to be normal force in minus nothing that points out. So the radial direction there is just going to be, sum of the force in the radial direction is just normal force 3 equal to mass times radial acceleration. Number 3, so normal force 3 is equal to mass times speed 3 squared over the radius of curvature, which we just called r, of the loop. And then number 4, the sum of the forces in the radial direction, is equal to, let's see, in toward the center of the circle, that's down. And we have 2 forces that point in toward the center of the circle. They'll add together. And there's nothing that we need to subtract off pointing away from the circle. And so the sum of the forces there is equal to the sum of the gravitational force and the normal force 4, because both of those forces point in the same direction. And that's got to equal to mass times acceleration in the radial direction. And the gravitational force there plus the normal force 4 is going to be equal to mass times the speed at position 4 squared divided by the radius of curvature of that loop, which we called capital R. So there are 4 equations of motion which highlight the principles of how to apply Newton's second law to something moving in a circle. It's still net force equals mass times acceleration, but now we're choosing to add up the forces that point in minus the forces that point out. So it's in minus out. In toward the center of the circle minus out away from the center of the circle is what I mean. And we have an equation for how big that acceleration needs to be. It's speed squared over r. I want to answer a question that is often on students' minds at this point in this discussion, which is, how come the box doesn't fall here? There's 2 forces pointing down, nothing pointing in any other direction. Shouldn't our box fall? And the answer is no. Why not? Well, if we were just to put a box here at rest, no doubt it would fall. That's the correct thought, no doubt about it. However, this box isn't at rest at this point on the loop. Instead, it's going around and it's in motion here. If the left half of this track vanished, if it were gone, then this box would shoot off like a projectile from there. And so what this box tends to do, its inertia would want it to do, is it comes around and then fires off like a projectile. And so we don't need a force to prevent it from falling, because it doesn't want to fall. It wants to launch to the left. What we need is a net force to prevent it from launching to the left. And it's these 2 downward forces that prevent it from launching it to the left and instead keep it along its circular path. So the reason this box doesn't fall is because that wouldn't be what it would do in this case. Instead, it has a speed to the left, so it naturally, in the absence of force, would go to the left. And so we need forces that are perpendicular to that leftward velocity to keep it turning in the circle. The other question that I want to address here, rather, the other physics coded language that I want to explain is sometimes it'll ask, at what minimum speed will the box fly off of this hill instead of going down? Or similarly, it might ask, what minimum speed does the box need in order to make it around the loop without falling before it gets to the top? So that's coded language. So the question is, what minimum speed is needed to stay on track? Actually, it depends on the situation. If we're looking at free body diagram 1, it's to launch off hill. And 2, it's to stay in, if we're looking at free body diagram 4, it's to stay in the loop. Either way, the way you answer the question is the same, which is launching off the hill or just barely making it around the loop means that we have lost contact with the surface. So we consider these scenarios, specifically scenarios 1 and 4, when the normal force is equal to 0. Because if we're launching off the hill, we don't have contact with the hill anymore, so the normal force is 0. And if we are just barely staying in contact with the loop, that means that the normal force is maybe just above 0, so 0.0001 newtons, which we can round to 0. So the minimum speed to stay in the loop or the minimum speed to launch off the hill, that's both coded language for look at those same free body diagrams, but the normal force is 0 because we're considering what happens when we lose contact with the surface. All right, folks, that hits most of the key ideas of uniform circular motion. If you have, or not uniform because that object is changing speed, but it hits the ideas of circular motion. Please let me know what questions you have. I am happy to help out.